So let's take another problem. This is a very classical problem. There will be a maze which is given to you, and let's say it is an n cross n maze. Okay, I'm just trying to give an example. Let's say this is the maze which is given to us, and this is a 4 cross 4 maze, and let's say these are the values 0 0 1 1 0 0 1 0 1 0 1 1 and 0 0 0 0. One thing is for sure, that any cell will either contain 0 or 1. And what is the meaning of 0 and 1? 1 means that the cell contains poison in it, and 0 means that the cell is safe. Okay, now what is the question? Question is that I consider this one, which is my topmost left corner cell, as 0 0, and I consider this one as my n-1 comma n-1. Now there is a rat which is sitting over here. So a rat is sitting at 0 0, and now this rat wishes to come down to this cell which is n-1 n-1. Okay, this is my target. Now rat has got two kind of movements. Okay, there are two moves that are supported for rat. First move is that rat can either move 1 unit right from current cell, or it can move 1 unit down from the current cell. So mathematically it means that if rat is at I comma j, it can take one step in right direction and move to a cell called I comma j plus 1, or it can take one step in bottom direction and move to something like I plus 1 comma j. Right? So these are the different kinds of moves that rat can take. Now this is very important. These kinds of moves that I have told you, this is very important, and you should automatically start drawing certain diagrams in your head. Okay, this means that if, let's say, at any point of time, let's say rat is over here, can it go here? Can it take a move to go back? Is that possible? No. But can it go right? Yes, it can go right, because the only two moves that are supported are 1 unit movement in right direction or 1 unit movement in bottom direction, right? So what is the question? Question is to print all possible paths. Print all possible paths that take the rat from 0 0 to n-1 n-1, and they should be distinct also. So print all unique possible paths that take the rat from 0 0 to n-1 n-1, adhering to these constraints. So tell me one thing first, how many paths do you see here? How many paths are there which is going to take the rat from 0 0 to n-1 n-1? Somebody said that there are 0 paths. I'm not sure why you said that, because I can clearly see one path is there, like this, and then like this, and then like this. This is one path for sure. Is there another path also which could take the rat from 0 0 to n-1 n-1? Again the answer is yes. So if rat takes this move, then this move, then this move, and then this move. So this was first path, and this was this was my first path, and this was my second path. So now how to print out the paths? So can anyone suggest me, like just use your common sense and try to tell me if I have to print any path. Let's say I call the first path as P1 and second as P2. How do you print a path? Coordinates. Yeah, you can simply print out the coordinates in the order in which they have been traversed. So that was a common sense, right? So if I talk about first path, which is this one, okay, there I would have wanted to print 0 0. After 0 0 you go to 0 1. After 0 1 you come to 1 1. After 1 1 you come to 2 1. Then 3 1. Then 3 2. And then 3 3. So this is my path 1. Similarly, I would have a different path 2. So in a new line I have to print a new path, which is nothing but a set of coordinates that have been undertaken in that path while moving from 0 0 to n-1 n-1, following the constraints that you can move 1 unit right or 1 unit bottom at any time. Okay, so first tell me one thing, for printing something like this, which kind of data structure would you want to use? What would you want to use? A vector array? Yeah, vector of pairs. Can I use a vector of pairs? Yes, I can, because there are many pairs. Each coordinate or each cell can be thought of as combination of I comma j, which is x-axis, which is x coordinate and y coordinate of that particular cell, and that can be accommodated in a pair of integer comma integer, and there will be many such pairs. So every path can be simply represented in a vector of pairs, where the pair is of int comma int. Okay, cool. Now think how I can solve this problem. So guys, at this point of time, it is very easy for me to tell you the solutions and everything, and you will understand and all. But the most important point is that you should be able to develop an intuition on your own. Okay, that is the most important thing. So let us understand how can I get my job done. So see, the question asks me to print all possible paths, and all those paths must be unique. Okay, so let us understand few important things over here. Okay, so tell me one thing. I'm just redrawing this. Okay, so let's say this was my maze, and I was here and I had to reach here. Okay, so see, all the paths that start from here and reach here can be broken into two categories, category 1 and category 2. So see, this kind of classification you have to do first, then only you will be able to divide your one recursive call into multiple recursive calls, so that whatever is going to come out of one recursive call is never going to appear, is never going to actually reappear in second recursive call. Okay, can you relate what I am saying? That is the thing that I have been doing from the beginning, right? While finding all the combinations or permutations or whatsoever, right? So can you think of the two categories over here? Two categories of paths. So I can say that, hey, one category of path will be those paths in which the first move was a right move, and second category of path will be those paths where the first move was a bottom move. And can it ever happen that a path of category 1 is also present in category 2? It can never happen, right? Because you take any example, so a path like this belongs to category 2, right? Because see, at the end of the day, every path can be thought of as a string. Okay, for right movement I am saying R, and for down movement I am saying D. Okay, so corresponding to this path I could have said that, hey, this path is like D, which is down, this is for right movement, and this is for those paths where first move is a right move, and this is for those paths where first move is a down move. So this path where first move is down would definitely come in this category, and it can be written as D down, and then right, and then down, and then right, and then down, right? So basically any path can be written as a string of R and D. So if you understood this, then it is very natural to understand it that all the paths coming in over here will have their first character of string as D, because their first move was a bottom move. So anything here can never appear over here, because whatever is over here will have first move as R. Okay, so let's say its first move is R, then again R, then down, then R, then down, then down. Okay, now just tell me one thing. If you are able to uniquely determine all the paths of this category, and you are able to uniquely determine all the paths of this category, then you simply have to print all the solutions from here and all the solutions from here. That is what you are supposed to actually do. Now let us understand, how do I get that done? Okay, how do I get that done? So for that, listen to one thing very carefully. Okay, so try to understand this thing first. Let's say, so to make things simple, initially I am considering a maze where all the cells are safe to travel. All the cells are safe to travel means all the cells are going to be 0. Okay, so let's say the rat started moving from here, Now its first move was to make a right move, and so there will be a class of paths that reach from here till here, okay, and all those paths will be having their first move as this. So they will all be different from those paths which reach from here till here and had the first move as this, right? So let me first make a recursive call to print out such kind of paths whose first move was a right move, okay, and then I'll go on to the second class of paths where first move was a bottom move, okay. Can I say one thing for sure, that no matter whether you have taken your first move as right move from cell I comma j, or you have taken your first move as bottom move, all the paths that reach from ij till here will definitely contain I comma j in the sequence of coordinates. Can I say it? Right? Because if there is a path that originates from I comma j and reaches the destination, no matter how you go, that path would definitely contain I comma j in it. Okay. So think of it in this way. Then what comes to your mind? Then in your mind this thing should come, that there must be a vector like this. There must be a vector like this. So see, one easy way in which I can solve this problem is by creating a new copy of this vector and passing it every time. But again, that will end up exhausting a lot of memory. So can I use a single vector to print out all the paths? Can I do that? Yes, no? Yes, I can do that very easily using the concept of backtracking. So think of it in this way. So whenever you are at I comma j, so what does it mean? Like if a function call for I comma j is made, what does it physically mean? It physically means that you are interested in determining the paths that start from I comma j and reach n minus 1 by adhering to the rules that you can either move 1 unit right or 1 unit bottom at every time. Okay. So you have to somehow use this particular thing and then try to get your problem solved. Okay, so let us try to understand. If you are over here at a cell I comma j, then whatsoever is your vector, in that vector you will first want to push back the cell I comma j, okay, and after pushing this cell I comma j, now you would make the recursive function calls for right move and down move, okay, because all the paths that start from your right cell, which is I comma j plus 1 and reach here, will definitely contain this in them, right? So now after pushing this, you would want to make a function call for I comma j plus 1. This is just like your right move. Okay, now when this function call terminates, what does it physically mean? It physically means that you have been successful enough in printing all the paths that start from I comma j, takes a right move and reaches here. Okay, so after this, what would you want to do? Can somebody tell me? After making this function call, what should be your next thing? Now you would want to print out all the paths whose first move was a down move. So to do that, now you would want to make a function call corresponding to I plus 1 comma j. Now tell me one thing. Before making this function call, would you want to perform an undo action or something? Would you want to pop what you had pushed? So one of you is saying to pop. Think again, think again. I had explicitly said it. All these paths that start from I comma j with a right transition and ends here will definitely contain I comma j, and all these paths will also contain I comma j. So does it make sense to pop it? No. Okay, it does not make sense at all to pop it. So what should I do? I should simply make this function call. And now when this function call is over and when this function call is also over, what does that literally mean? That literally means that, hey, I have printed all such paths that start from I comma j and end at here, whether they are of this category or they are of this category. So when you have done that, now you are free to undo your action. What was your action? Your action was to push I comma j, because you were trying to explore all the paths from I comma j till the end. But now once you have printed all of those, your last line of code should be to pop it. So vector dot pop simply vector dot pop. whatever you had pushed. So I will give another picture of it which will make your understanding even better. So just think of it in this way. When you are recursing, okay, so let's say this was your grid, okay, this was a grid that you had, and let's say you reached at any cell here, okay, let's say this was I comma j plus 1, okay, so you would have reached here either from this cell or from this cell, isn't it? You would have reached here either from the left cell or the upward cell, right? So for a few time, let us assume that you reached here from here, okay, so this cell would have been I comma j, okay. So when you were at this cell, you had two options. What was the first option? Either to move right or to move bottom. First you preferred to move right because first you want to print all the paths that reach from here to here by making first move as right move, and then you will come down to this. Now when you are here, again you would take two moves, this and this, again you would take the two set of moves. So basically what is happening, that all those paths that start from here and ends here, considering the fact that you came to this cell via this cell, will definitely first contain I comma j, and after I comma j will definitely contain I comma j plus 1. After it can contain these variety of cells, okay, where your move was either right or down and so on and on and on. So eventually what would happen when you have made the right call and bottom call also from this cell? So when you are at this cell, first you pushed this cell I comma j plus 1, then you made a right move, then you made a bottom move. When these two things are over, what would be the last thing that you would want to do? You would want to pop this thing out, right? Because only if you pop this thing out, then this thing goes away, and then you just have I comma j with you. Now you can come from here to here, and now when you are here, you can push this thing. What is this thing? This is I plus 1 comma j. And now then you can start printing all the paths that start from here and reach here by taking all the right kind of paths. So the point that I made was, whenever you are at a cell, you first push it and then you recurse in right direction and bottom direction without popping it, because it is guaranteed that all the paths that start from here and reaches here, whether it was right or down first, will contain I comma j. But after you have printed them, then you want to pop it out. Why? Because whatever was your parent, that no longer needs you now. Now that needs this cell to be pushed, right? So can you implement it then? Let's take a look again, okay? So I am going to draw a tree diagram for this, and that will give us a lot of confidence in coding this thing, okay? Yeah, let us take a very simple kind of maze to start with. So this kind of maze where everything is 0, 0, 0, 0, 0. Okay, I take this thing to start with. So you will start your journey with a vector of pairs, and that vector of pairs initially will be empty, okay? And then you will start your journey from which cell? Can you tell me from which cell would you want to start your journey? What will be your initial I comma j? It will be 0, 0, okay? So you will start with 0, 0, right? Okay, great. Now let us assume this function call has been made. This function call has been made. So what will you do first? What will be your first action? Whenever you reach a cell, what do you do first? You first push that into your vector. Because what is the physical significance of being here? The physical significance of being here is that you wish to print out all the paths that start from here and reach here, following the rules, okay? So all those paths will definitely contain this cell in them. So your first action will be an action of push. So when you push, what is going to happen is that this will start containing 0, 0 pair inside it, okay? Then your next action will be to move to right, and after moving to right, what will be your next action? To pop. Will it be to pop? No, it will be to move down, and after down, then you will finally pop, okay? So let us do that one by one. So after here, okay, now what would you want to do? Now you would want to make a function call where you would want to go to the right cell. What are the coordinates of right cell? That is 0, 1. So you had pushed, and this is a pass by reference. So whatever you had done over here will get reflected in the temporary vector that is passed over here. So it will contain 0, 0 in it, and it would show that now you are at coordinate 0, 1. Okay, so now you are over here. Again, what will be the first thing that you would want to do over here at 0, 1? Again, what should be the first thing that I should do? First I should push. Okay, and what should I push? I should push this 0, 1 because all the cells that start from here and reach here will definitely have 0, 1 in them. So my first action will be to perform a push. Okay, so when I perform a push, then this vector will get converted to 0, 0 and 0, 1, right? After having done this thing, now again when I am here, how many options do I have? 2 options, move right or move down. So let's say I move right. Okay, moving right means what? That I'll pass this vector which will be containing this, okay, and I will move to a cell called 0, 2. Now let's talk few more things. Let's say you were here, so first you push and then you made a call. Okay, now once this call is over, then you would have made second call, wherein you would have moved to where? You would have moved to 0, 2, right? So you would have moved to from here till here. Your down move would have taken you to 1, 0. Okay, and now when you move to 1, 0, would you want that the vector which is passed over here, that vector contains 0, 0 and 0, 1? Would you want that? You would not want that. Why? Because in that path that doesn't come. 0, 1 doesn't come. What comes? Only 0, 0 comes, because that is the parent. That was the last cell where you were at. So you would just want 0, 0 to stay over here, and it will happen. Why it will happen? Because when this thing is over, then when this entire function call is over, then its responsibility is to perform a pop of what it had pushed. Okay, so the last thing that it will do before returning to this would be to perform a pop of this thing. Okay, a pop of this thing which it had pushed. So what it will ensure that when that pop is done, then after making this pop, you will just have 0, 0 with you and not 0, 1 as well that you had over here. Okay, now again, so this is how it will go ahead. What would be your last action over here when you have, let's say, performed this thing also? So again here your first action would have been to push this. Okay, and when this is all over, before returning, you would perform a pop. Now when the control comes here, so its push is done, which was this. The function call for this thing is done. The function call for this thing is done. And then the last thing would have been to pop. So eventually you see that when the function returns, what was your original, temporary vector that was empty. And now when the entire thing is over, your temporary vector again is also empty. So you can draw this on and on, but it is going to be a very big diagram, so I would avoid drawing it. If you want, you can just continue drawing it. Okay, by the way, tell me, so now let's say you are here 0, 2. So now this denotes that you have taken this path, and now you wish to print all the paths that make you reach from here till here. Okay, now how many options do you have here? Can you tell me number of options? Do you have 2 options? No, you just have 1 option. And what is that 1 option? That 1 option is to move down, because you cannot move right at this point of time. Okay, so this is one edge case that you have to handle. So whenever you are in last column, then you just have 1 option. Okay, similarly, whenever you are in your last row, how many options do you have? Again, you just have 1 option, which is to move 1 unit right, because you cannot move 1 unit down over here. So these are some edge cases that you have to handle. Okay, so corresponding to this and corresponding to this, there will be only 1 move. Okay, what can be some termination conditions? Let's say you happen to reach at a cell where the value was 1. It means that there was a poison over there. So what should I do at this point of time? So whenever you are at a poisonous cell, you are saying that you want to know how many paths are there which are extending from poisonous cell to n-1, n-1. Will there be any path? No, there will not be any path. So you should not let your recursion tree go down further from there. You should simply return from there. So that is one termination condition. But there can be one more termination condition where you have reached your destination, isn't it, guys? Yeah, where you have reached your destination. So how do you identify whether you have reached your destination or not? When your I and j both are equal to n minus 1, that means you are at your destination. So at that point of time, you will simply print your path and you will return. So these are the two termination conditions which are in the scene. What was first termination condition? That Aij was equal to 1. Okay, so here you simply return and don't go down further. And second termination condition was that your I and j both were equal to n minus 1. So here you print the contents of your vector and then you simply return. So let us understand, if I have to write the code of this, how do I go about that? So let us see, there will be a print path methods, which is a void. It takes in a paths variable, okay, and it takes in I and j, okay. What is this paths? This paths is this vector of pairs, okay, and this I comma j is whatever coordinate you are at. So what should I write first? I should first introduce my termination conditions, right? So yeah, if I is equals to j is equals to n minus 1, what does it mean? It means that I have reached the last cell. So what will you do at this point of time? Will you always print the contents of vector, or can there be an edge case here also? It can happen that you have a poison here also, isn't it, guys? Right? It can quite happen. So in that case, you would not want to print it, right? So you will check that if at this point of time you saw that a of ij was equal to 1, then you would simply like to return without doing anything. Okay, you would simply like to return. Otherwise, what would you want to do? Otherwise, you would print the vector, you would print the contents of vector. Now one thing, the contents of vector would not contain this cell in it, because you perform a push when you reach at I comma j. So while you are at n minus 1, your vector would not contain the last cell's coordinate in it. So instead of pushing and then printing and then popping, what you can simply do is that you know that, hey, you are already at destination and you have the list of all the previous cells in your paths variable. So you can print that vector, you can print that paths, and after printing it, you can print two more values, which is n minus 1, and after that you can return. Okay, what can be other termination condition? Other termination condition can be that I am at some poisonous cell. So if a of ij is equal to 1, I am at some cell which is not the last cell but that contains poison in it. So I should simply return from there. Okay. Otherwise, what should I do? Otherwise, it means that I am neither at destination nor at some poisonous cell. So I am at a safe cell which is not poisonous one. So how many options do I have? But will I always have two options? No, it depends upon whether I am in the last row and last column or not. So I need to handle those edge cases of last row and last column, and I think I can handle that very easily. So if I see that I is equal to n minus 1, I equals to n minus means that you are in the last row. So if you are in the last row, then you will have just one choice to make. But before making that one choice is like calling the function. Okay, so before making that, the first thing that you will do should be what? To push this particular coordinate, which is I comma j. So the first thing that you would do is you would do paths dot push back I comma j, right? And after this, now you will recursively call the function and you will just move to your right direction, which is I comma j plus 1. And when this is over, then you would want to pop. So paths dot pop. Okay, so this was the case when you were in the last row. So similarly, will I have a case for last column also? The way I had for last row, will I have a case for last column also? Yeah. So for that, what will I write? Else if I see that j is equals to n minus 1, that means I am in the last column. So the first thing I will do is I will do paths dot push back I comma j, Okay, in the last column you push that cell and now you move down. Moving down means what? Calling the function for I plus 1 comma j. And after this, what would you want to do? You would want to pop whatever you had pushed. So paths dot pop. Okay. So is it done, or do I have one more condition which is left? Yes. And what is that condition? That condition is when what? When I am at a safe cell, and that safe cell neither is in last row nor in last column. So in the else case, what would you want to do? Tell me. You would first want to push that. So you would do paths dot pushback I comma j. After this, you can either move right or you can move down. So moving right means calling this for paths I comma j plus 1. Would you want to pop after this and then call down? No, right? You would simply want to call down I plus 1 j. And when this is over, then you would want to pop what you had pushed. Now there are certain redundancies in the code that you can very well clear. First redundancy is that before the recursive calls in this if or this else if or this else, first thing that you do is you perform a path dot push, path dot push, path dot push. So this path dot push logic can simply lie here, and path dot pop logic can simply lie here instead of lying at front and ending of each of these blocks. It can simply lie here and here, and if else conditions will just have the function calls in them. Okay, cool. So this was the way. Again, it's a classical backtracking. Important thing to be kept in mind is just this, that you should know when to undo. Okay, if you know that the choice that you have made will prove useful for certain other set of actions also, why pop it immediately? Pop it when it is actually required to be popped. Okay, and that you have to, that thinking you have to start germinating on your own. Okay, great.